Dr. Alejandro Barbero, who is also co-organizing this event of two talks. The other talk was yesterday. Dr. Alejandro Barbero is in the Institute of Nuclear Sciences at the Laboratory of Chemical Evolution, and he's the vice president of NoRCEL. And me, I'm a postdoc with Dr. Marco Jose at the Theoretical Biology Group. And well, that's my naming at NoRCEL. Yes, I'm currently the president. But what NoRCEL is? Well, actually, NoRCEL is an interdisciplinary collaborative network founded by Dr. Jheeta in 2013. We understand the NoRCEL as the emergence, evolution, and extinction of life. In a moment, this will be clearer. Our primary aim is to bring together scientists from various disciplines to investigate one of the most fundamental questions of science, how life began. We are a truly global network of scientists, researchers, even students, and lay people coming together to work and investigate the fathom of some of the most multifaceted aspects and most elusive challenges in the scientific world, facing the scientific world. Our most recent missions are exploring global issues. For example, with our Blue Earth project, PEP, for abbreviation, and we also try to developing educational tools in our endeavor, especially in what is called the Global South. For example, Latin America, Sub-Saharan Africa, South Asia, Sub-Indian continent, etc. So, the prime objective of NoRCEL is to promote and disseminate research information related to the chemical evolution of life on Earth, from the advent to prebiotic chemistry through the emergence of the principal cellular life forms and eventually its extinction. The roadmap of NoRCEL began in 2013. NoRCEL began as the network of researchers on the horizontal gene transfer and the last universal cellular ancestor. Very long name, I know, but it's focused on studying the role played by the horizontal gene transfer and its fine-tuning to Luca's genetics. Later, in 2016, Luca, in the name, acquired the common accepted meaning, universal common ancestor, instead of just cellular ancestor. Later on, in 2019, the name transformed into the network of researchers on the chemical evolution of life. But 3 years later, on November 2020, after a broad consensus with many of the members of NoRCEL, NoRCEL becomes from the chemical evolution of life to the network of researchers on the chemical emergence of life. Why? Because emergence is more than the sum of the parts. The emergent properties create something more complex. Now, NoRCEL will be transformed for the sake of the community. The characteristics of the innovative initiatives of NoRCEL are, for example, sending invitations by email to the different NoRCEL events, to Origin of Life scientists, of course, but also to those who are not necessarily involved directly in this research. For example, you are welcome to join to NoRCEL as biomedical researchers. And one of the characteristics is giving voice to talent. All those who address each other with respect and science will have a voice, regardless the ethnic, the nationality, or the academic degree. The conferences are in person, mostly of them, and others are hybrid, but always are excellent offered. For example, with unconventional sightseeing for in-presence conference. English is the lingua franca of science, so the conferences are offered in English. And also the conferences organized by NoRCEL doesn't last for more than 3 days and no more than 6 hours per day. in order to avoid the exhaustion of the mind. And they are also streaming via Zoom. And also, the most important thing for NoRCEL is that we are based on a concept that Marco Jose coined, that is the horizontal ideas transfer. In biology, we have the concept of horizontal gene transfer, but now in NoRCEL are implementing the horizontal ideas transfer. That, by the way, is the way that we at the theoretical biology group, headed by Dr. Marco Jose, following all the time. We are based on horizontal ideas transfer, regardless the academic degree or nationality, always based on arguments based on science. And we have also strategic operations. Then, some of the results in NoRCEL are all of the investigators who belong to the network, for example, Dr. Marco Jose, Dr. Sohan, Jheeta, myself, all of the members published regularly in most of the high-quality journals. For example, bioessays, for example, biosystems, theoretical biology journal, etc., or some of the publications by MDPI, etc. Even some of the research of the members have published in Nature or Science or scientific reports. Moreover, NoRCEL has published conference reports of the congresses and reviews on outreach activities that have been achieved. There is a list of the conference reports and about the outreach activities that NoRCEL, headed by Dr. Sohan Jheeta, has done in Africa. Additionally, several students from all over the world have been supported. Actually, let me talk you to my own experience. I was on my first year of my PhD, and I went to a congress in San Diego, California. Then I applied for a scholarship provided by NoRCEL, and I was awarded with that scholarship. So I could be there in San Diego, California, and to avoid to expense a lot of money, a lot of my own money, because NoRCEL supported me. And that way I met Dr. Sohan Jheeta, I met there in San Diego, California. Because NoRCEL is based on an attitude of service. So, yes, we love this for the love of science. NoRCEL is a non-profit voluntary group, not on-demanding, that's not mean. But this is independent of any academic institute or private organization. It's currently supported by our own resources, mostly from its founder, and all initiatives wouldn't thrive and flourish without the support of our small voluntary international team members and proactive unpaid members. NoRCEL is also an organizational member of the Royal Society of Biology. But at the present day, NoRCEL works as an operational umbrella, under which many other projects and hubs develop, while maintaining its own activity of organizing events and publications, both academic and outreach. For example, the hubs are independent and they are prosperous. We have the Latin America hub, which I'm also the head, and NoRCEL sessions. But also we have projects which are not independent of the umbrella yet. We have the Blue Earth project that is regarding the evolution of life on Earth or climate change. Astroscience Exploration Network, named ASEN, which is for disseminating science in Africa. We also have the Microbial World Network, headed by Dr. Oleg Kozyurbenko, which is from Russia, living in Germany. Our NoRCEL motto is emergence, as I told you, evolution, and extinction. Emergence is regarding the origin of life as the most principal focus. The evolution is about microbiology and microbiotas. But the extinction is also very important to us to know how the future of life on Earth will be done. We organized the Blue Earth project about environmental change. And we also published an online magazine called the 3E, the Emergence, Evolution, and Extinction, because a good read is a stuff of potential power. So I also invite you to publish with NoRCEL under the Tree magazine in no more than one page article of no more than one page. It's principally an outreach article, science communication, actually. Well, the perspectives of NoRCEL are generate our own resources, prosper the projects, and to transform them into hubs. And we need people who take the wheel. So NoRCEL will gradually transform from only an academic community into a scientific institute for education at low or free cost for low and middle income countries' students. So we together can make NoRCEL grow. So these are our social media. They are also in the bookmark that I handed out to you, but if you don't have a bookmark, I will give you one. So finishing talking about NoRCEL, I will tell you about, I want to introduce you to Dr. Sohan Jheeta. Well, Dr. Sohan Jheeta completed his PhD in prebiotic experimental chemistry and founded then the scientific group now named NoRCEL. In order to extend the scope of collaboration about various disciplines, as I told you, trying to solve how the life emerged. But his aim is to discover the exact origin of life, and by extension to determine whether or not life could be made in a laboratory. Being resolved to find the answer, he is currently the chairman of NoRCEL, and it's many groups like the Blood Meridian Boulevard Project, Latin American Hub, Astroscience Exploration Network, ASEN, or the Microbial World Network. He is also a STEM ambassador in the Yorkshire region, and he's also an educator and science communicator. He has carried over 120 national and 113 international outreach programs, including workshops, and he's been able to help over 20 students from developing nations in terms of bursaries and personal awards, as I told you in my own experience. He also has donated some telescopes to some African countries, for example, in Zambia and Malawi. He also donated a Fourier transform spectrometer and software for experimental purposes in Tanzania. Just a moment, please. Oh, my throat is dry. Sohan Jheeta has written over 40 peer-reviewed scientific papers and 4 book chapters, as well as published 2,000 journals and visit over 4 institutions worldwide, where he delivered scientific presentations. I don't know what's happened. Could you help me? Okay. He's also in the editorial board member of MDPI Life's Journal and an advisory board member of their journal named C. He has also reviewed numerous publications and has been guest editor in 4 occasions. Recently, he has been appointed as an academic editor of Hindawi's journal, Advances in Astronomy. He is also a prolific speaker and promoter of science. He has given 8 keynote speeches and more than 100 oral presentations, and also has presented 30 posters internationally. To the date, he has also organized 20 conferences and 8 lectureships on behalf of NoRCEL, as well as the Royal Society of Biology and the Royal Society of Chemistry. Finally, he is an active member of the Institute of Physics, the Royal Society of Chemistry, the European Astrobiology Network Association, and the Royal Microscopical Society, as well as a fellow of the Royal Society of Biology. He has also undertaken 40 self-development and training programs in order to keep abreast of the latest developments in scientific era. Dr. Sohan, please.
Thank you very much, Miriam. That was a pleasure to hear that. Actually, I didn't know all those things. Thanks for the reminder. I'm going to put this in to use my PowerPoint.
I can't.
Anyway.
I will switch off this.
You wouldn't get me there. You see this? And then
We changed the presentation.
I'll be able to change using this.
Oh, okay.
Yeah.
Okay,
Yeah.
perfect. I'm ready.
Mm.
Ya no puedo salir.
Yeah.
Sí.
I'm going to use my finger.
Oh God.
Okay, just take.
¿Es el yo? No es yo. Admíteme, pero no sé cómo moverme. Ya te metí según yo. Pero ahora no se ve aquí. No puedo ni- No quiero escuchar la cancioncilla.
I'll take the pointer out, then leave it. I'll use my finger to change it.
No, it's okay.
The problem is that
Yes.
the signal doesn't go to
Yeah.
the screen, to the big screen.
Yep.
HDMI.
No se me olvida abajo. Que ya está fallando. ¿No reinicio? Como siempre.
Dios. Sorry for the inconvenience.
And should not.
Shouldn't have done that.
Tu esposo que te va a enseñar que no sé.
I think we should remove this altogether, right? Remove this. It's likely interfering with it.
We will restart the projector. Ay, ese señor. Porque ya no prende el proyector. Ay, no sé. Ya no prende. Ahí está. Ya. No, no conecta. No, no está conectada. No sé. ¿De qué te lo dice? ¿El USB?
El HDMI ya está.
Sí, es que no está bien conectado.
no, es la que no jala.
Ujú. Ujú. No,
Pero
el problema es el HDMI.
Ah, ya. Chicken is sugar.
Yeah, sugar, sorry. Es el cable, porque hace lo que lo tengo que mover para que conecte.
There's two slots there. Look, Jay, is it just one? Oh, yeah,
HDMI.
yeah. I'll tell you what, I still think if that's interfering with it, let me just take it out because that,
Okay. Then try to.
yeah, yeah,
I don't
No.
think so.
we,
Que hay una para
Reach
cambiar la
out.
pantalla, ¿no? Con la función esta. ¿Es esta? Es que no-
Pero es el HDMI, no lo lee.
O sea, es el problema, es el HDMI.
es que hay una función para cambiar la pantalla aquí. Creo que es esta. Pero tampoco quiere hacerlo.
Si te das cuenta, está como chuequito. Mira, pero.
Y por favor, es muy alto. ¿Vale? No hubiera presentado la pasada. Ya estaba todo bien.
¿Tiene el control?
Sí.
Ya lo apagaron bien, ¿verdad?
Ya se volvió a pagar.
if you're going to restart that as well.
No, pero no,
The problem is the cable.
Okay, all right.
That's the problem.
Mm.
Because it was working, but
I know what and what. I wish I hadn't said anything, kept my mouth shut and get on with it.
o si estamos con su compu. Pues podría.
Pero
Bring
si el
your
problema es el
laptop,
cable,
please.
Es que como que se centra.
Your laptop,
O
please.
podemos, como en la pantalla no podemos usar la pantalla.
Use my
de
laptop.
No sé cómo usarla tampoco. No.
Use my laptop.
Perhaps.
Yeah, if you want.
We can
Yeah.
try. Es que no quiere.
lo que muy bien.
O sea,
Ya no quiere ni prender, pues esto.
no quiere. El problema es que ya no quiere agarrar esto. Abajo, para arriba.
Pues ahora quitan esta información para que se
El problema es que yo tengo la reunión de Zoom.
Mítelo ahí y lo pones como co-host. Y ya. Admítelo ahorita que entré.
Okay, let's,
HDMI.
yeah,
Yeah,
got it.
it's there.
Ouch.
Microphone. It's there.
la cierro. ¿La cierro?
No,
Así la dejo.
no, not the same. Wait. Yeah.
Wait, yes.
Yeah. It's
All right.
so.
Me dejo el link.
So look
Yes. So
Start video. Start video.
video
Yeah. Look your
and
people can look you.
this one. I think it's this
No,
one.
it's the other.
Look, we got
It's
it.
the other.
We got it.
No, it's the other.
No, it's on there.
Ah, okay. But this is not. It's the other.
Hmm.
Let me.
How
Please.
come there's so many of them? Oh yeah, okay.
Gosh. Well, they can see that.
Oh, right, okay. All right, let's start again.
Recording in progress.
Third time. Thank you very much for being here. So all I want to say is that there is a conference in Nigeria. We're hosting together collaboratively, and please do join us on the 27th and 28th of August. We look forward to seeing you there, but let's get on with what I'm supposed to do. It's
Don't freak. I hope I can help you. Okay. Wait. Is this? No. Is this? No, it's not. It should be this. Bueno. Ujú. She will share your presentation from that computer,
she'll share it.
and you will keep talking from here.
Okay, all right.
Stop
Let's
sharing.
see.
So,
All right, okay.
Recording stopped.
Okay, so today I'm
that's all.
I'm going to talk
Recording in
about
progress.
carbon chemistry. We're really excited about this new chemistry, actually. Although it's been around 50 odd years, it was discovered actually 70 odd years. So it was actually discovered in the 1950s. So carbon chemistry may not be the be all and end all for the emergence of life. So let's go how far we can go. Next, please.
Recording stopped.
Are you able to go to the next slide? All right. Did you do that or did I do it? Oh, I can do it. I can do it. I think it's working now. Yeah. All right. Thank you very much. So what are reactive oxygen species? They're reactive, although made biologically, these reactive oxygen species, but we're not really interested in about the being biological.
Recording in progress.
Of emergence of life, there was no biology. So therefore, I'm interested much more those species that were made in the during the abiotic era of life's emergence, about 4.3 billion years ago on the planet Earth, and ROS are considered more potent than other reactive species. When I say that, I don't know whether, are you able to see, Gabby, are you able to see my pointer?
Yeah. Your pointer, yeah.
Yeah, no, on the computer. Are you able to see my pointer?
No,
Right, okay. Number two being that more potent, reactive oxygen species are considered to be more potent than the reactive species of other oxidized.
Recording stopped.
These are some of them here, but I got a better illustration in the next overlay. Oops. So these are the standard redox potential for oxygen species. They're far more potent. All other ones are, and number three being, in addition to ROS being, other elements are, for example, sulfur, chlorine, nitrogen, and carbon, they all generate reactive oxygen species. And so the question that arises is, can ROS be generated?
Recording in progress.
Answer to the question is yes. And so here are some facts about the oxygen before I begin. So to date, over 300 gas-phase molecules have been found in both interstellar medium and circumstellar disk. And here are some of the examples given here. And all of these molecules shown here, they've got oxygen in it. If they got oxygen in it, in one way or another, they could be promulgated or used as reactive oxygen species. And in another survey, 174 molecules in space, 48 were organic, containing oxygen. And oxygen is the third most abundant element in the universe after hydrogen and helium, as well as in the sun and Earth's crust. In the human body, oxygen is the highest in terms of mass, 65% of the constituent element. And of the 10 molecules present in the comets and protostars, you have 7 of them contains oxygen. Here you are in the table. And from the genomic evidence, hydrogen peroxide, H2O2, genes were present in the LUCA, and LUCA is last universal common ancestor. Did hydrogen peroxide help to kickstart life? Ball and Brindley in 2000 paper seems to think so. I'll say a couple of words about that later. That's the formula for hydrogen peroxide, or the Lewis, I should say, representation of hydrogen peroxide. And hydrogen peroxide has been found close to the star Rho-Ophiuchi, if I can pronounce it correctly. And here's another way of saying that it was published in physics.org in 2011. And so there's somebody called Sweetman in 2024 last year, discovered dark oxygen at the seabed, meaning that tons and tons of oxygen being produced in the seabed. And so there's something to think about that. Did that occur during the early period of Earth's history? It's a question mark, but the fact that it's happening now, I don't see why it wouldn't have happened then. And ROS was discovered in the 50s, oxygen being very electronegative form a highly reactive species, which may be instrumental to the chemistry or emergence of life. But bearing in mind, we're trying to discover whether they did do anything significant. So let's go on. So ROS were probably highly probably abundant on the early Earth. It's more likely to. But before I can do that, before I can tell you anything about it, you need to understand that the Lewis diagram, the one that you saw earlier on appearing with the hydrogen peroxide, is not the only thing. And because I can't see, I have to look at the PowerPoint all the time. What we have here is this. I'm going to explain to you how the electrons are placed in the orbital. This I'm going to speak about the from the perspective of orbital, not the perspective of Lewis diagram, the one that's shown here, these red balls, these kind of representation. So I haven't shown level number 1s. I have not shown that because the electrons in those level do not play any part whatsoever in the chemistry. So I'll begin at 2s, the second level. And let's put some electrons in that. Here you go. So this is in the first sigma bond, sigma levels here. So two are placed such that they're anti-parallel to one another. And then if I will carry on, the next sigma bond being formed, and the aspect, the star or the aspect represents, it's highly active or reactive. It's got higher energy. That's why it's above the ordinary sigma. And then I've continued to place these electrons here like so. This is the pi bond where the electrons are now being put in. And now this pi bond level is now full. So we've got just two left in the X 2p level, 2 electrons left. So I have to place those in the pi bond with star. I have to place these. So this is what happens. Here you got electrons going here. Currently they are parallel actually. And this is the ground state of oxygen. This is the stuff that you breathe, and it's called triplet level. It's what's represented here on the. Would that be if I did this? Would it be? No, it wouldn't work, would it? So it will be the oxygen shown on your right-hand side. That's the one I'm talking about, oxygen with O2. And if I were to go to the next and look what's going to happen. So what happened is that the previous slide overlay showed they were parallel. Now they're anti-parallel and they're in high pi orbital. This means that it has actually a very, very high level of energy. It's the most active state you can find. And and it has more energy compared to the previous overlay. That's what I'm trying to tell you. And we don't call this one triplet state. We call it a singlet state. And so the reason I tell you about this is this. It is this that lends this state that lends you energy necessary for the organic chemistry to transform into life. This is the one that I'm talking about. Of course, you can put it like this in separate orbital on the left and the right, anti-parallel. But you can also do this as well, where they're in just one shell. What that means is that it still has the same energy as the previous overlay, and so this means this also lends itself for energy transformation of other molecules or during oxidation processes, for example. And this particular electron that's coming in, I put in, that is actually from the environment. This particular one is from the environment. So what you got now is that this is called super radical. The reason it's called super radical is that so I'll go back. Oops. The reason it's called super radical is that at this level, when they're in one level, anti-parallel, this is actually called a free radical. This is free. It's very important to remember that this is a free radical. It has high energy. So, but if I were to move forward now, and this electron is filled from an environment in the other shell, the empty shell, now what it becomes is super oxide of oxygen. And this is shown, formally shown on your right-hand side, sorry, on the left-hand side, as you would be looking. I can't tell actually. But anyway, it says superoxide. So that is both free radical and ion. Now, to put together, they have more energy than the other previous ones. So So this is also involved in the very early chemistry. This would have been involved in the very early chemistry. And if you were to put another electron, because you can put in another electron, and this form peroxide ion, and which is above superoxide oxide, you can see that it's got a dot meaning that it's a free radical, and 2- means it's got double negative charge. And of course, if you were to add oh, sorry.
Sohan,
Hmm.
the carbon has a tetrahedron structure.
Yeah.
Is it necessary the tetrahedron for these changes on the electrons in the orbits, or is it irrelevant?
It's irrelevant. That's when you're looking at Lewis diagram, placing like this. It's
Space.
yeah. You have to. We don't actually draw it even like this. We draw it as some sort of bond, this space of balloons above them. But in this case, this is why I'm showing to you that this is the only way to explain how the electrons are distributed. The ones that are here, on the first one with the two anti-parallel red arrows, that's the free radical aspect. That means it will react with anything. That cannot be easily represented on the Lewis diagram or even in the clouds as well. It can be, but it's difficult. It gets complex. The bigger the molecule, this is a very big molecule. But if you're dealing with hydrogen, right, it's very simple because it's only got one electron, or in hydrogen gas, that's dihydrogen. It will have two electrons. It's very, very easy to fill these and show everything. But as the element gets higher and higher in number, then it becomes more and more complex. Of course, there's super guys who spend the time looking at these things all the time. They can do it. Somebody like me can't do it because I work on more lower basis, because I'm trying to understand chemistry as a whole, how it would be involved in the emergence of life. Yeah, I hope that that helps. But that comes into forming bonds. I just want to explain where the energy comes from. That's the only thing I wanted to explain in this aspect. Okay. And here's some on this chart. I show you the superoxide ion, and then of course people have classified all the red ones are called free radicals. Really, to be quite honest, every time you get this dot around it, that here, right, you can assume that it is actually a free radical, as well as when you have a oxygen right at the top. That actually tells you it's an ion as well, meaning that it carries a charge. In this case, it carries negative charge, and is a free radical. So it's double the effect. So it holds a lot of energy, and this is the one that will help us to understand the chemistry of the emergence of life. And the one in black below, those are the kind of a non-radical reactive oxygen species. But the point about that actually being included in here is that they are still involved in the reactions, overall reactions. It'll become apparent as they go along how it's involved. And but I consider them, all of them, to be reactive oxygen species, but some people are pedantic unnecessarily. And this is the Lewis diagrams, what I'm talking about here. Every time there's a purple electron you see everywhere, those are the electrons I'm talking about. And of course, the hydroxyl group has it just have a minus charge, but hydroxyl radical, the middle one where it says that's the super has more energy to give away. These are very difficult to represent on diagrams such as these. And so summary of the previous slide. Oxygen is the second most electronegative non-element after fluorine. In other words, fluorine is the top-notch element in terms of electronegativity. In other words, it's much more freer, but you don't actually consider, for some reason, nature chose oxygen. And it's also the highly oxidizing agent after fluorine. And I showed it to you, those positive charges, like I think in the very first slide. And then you have atmospheric molecular oxygen, that's O2, is sometimes also referred to as, and can be written as one, you put the superscript 1 and then 2. And so the point, another point about this oxygen, it is actually a singlet state I'm talking about in this case, in the third and the fourth bullet point. That's what I'm actually talking about. But it's made from oxygen, which is state. I wish I had put where it says oxygen O2 in bracket. I should have put a triplet state that actually, but I'm really talking about singlet state because it's the singlet states that has the highest energy compared to the triplet, which is just O2. So the singlet state is highly reactive due to having 2p unpaired electrons with anti-parallel spin, as shown right at the end of the sentence, and then spins, and then the other one is also having a parallel, but only in one of the pi bonds, star pi bond star. That also is highly reactive. And then the triplet oxygen, which I was talking about, also has 2 unpaired electrons, two unpaired electrons, but they're differentiated by parallel spin. The spin is, you represent, these are the quantum numbers. I'm not going to go through these. And these are called ground state, actually. The ones above, singlet, they're called excited state in comparison to one another. And every time oxygen is excited, we normally put star as well on the side to show that it's excited state you're talking about. Oh yeah, there is another, what I forgot to mention, which is very, very important, that these energies can be measured. You can actually measure these energy, but there is another state, a state below these excited state. And that state has a less energy, but nonetheless, it's still involved in the reaction. I wish I had put those in there to make some sense, but I do apologize because this is the second time I've given this talk, and each time I do it, I make it better. But because I can't see my own PowerPoint, there's a slight delay in my reaction. So this slide should not be in. It should not be included in this talk. But I chose to include it because there's something really, really important that you should know about the emergence of life, and which is this: that you've got shown what's called energy diagram for forming bonds, and you see that in the middle there is energy of activation written here. And then you also got same product form, that AA-AA dimer, it says there. And then the other energy is energy absorbed. This is very important reaction in biology, in the emergence of life, because this reaction forms what's called disequilibrium in life. We are at a disequilibrium. If I were to take a rock and heat it up, that hot rock would actually eventually energy would dissipate. It'll come to, I don't know, room temperature, whatever that may be, where it's lying. So whereas our body temperature stays the same, so it's deliberately kept there. And this actually is important when you're thinking about the emergence of life. And such reactions are called endothermic. They use energy. So the loop at the top is the energy that's being used. But below the line where the dimer is written, that's the energy being invested in the bond. And that is important because generally, if you were to take a match and strike, this diagram would be different in that the energy would be less because it strikes very quickly and the product would be down at the bottom. These reactions are very, very different. It means that you need energy all the time. All your reactions in your body and in bacteria, all the biology on planet Earth has these reactions going on in their bodies. So, meaning that each time they do this, they also generate water, and the question arises: where does this energy comes from? You know, which means this energy requiring a reaction, this particular one, and a water molecule is generated and process. We call that condensation reactions, but the life is believed to be originally started in a watery environment. So all this water being generated, that's kind of it gives the game away that it's impossible to carry this reaction out. But by the way, if a reaction such as this, any reaction in the body, any reaction at any time during the emergence of life, and this could not be worked out by abiotically, then life would not be possible on planet Earth. Okay, possible triggers for the formation of reactive oxygen species: UV light and radionuclides. Here are an example of radionuclides, and also smoke from volcanoes. A lot of reactive oxygen species are floating about in volcano plumes. And the early epochs, smog, did the smog mix available? I don't know. That's why I put question mark there. Smog is a word made up of smoke and and fog. Was there a fog during the early? I don't know. So it's a question mark. I'm sure a lot of other people would disagree that there wasn't around, but who's to say? We weren't around ourselves. So heavy bombardment by impactors generating huge amount of energy. When I talk about impactors, what I'm talking about actually is meteorites, Earth being hit by meteorites, being hit by asteroids and comets, right? You don't measure in terms of this is 300 kilojoules or even trillion kilojoules. The type of energy that these impactors generate is in the form of tons. These nuclear bombs that we have. Phenomenal amount of hundreds and hundreds of bombs, and as you know that in Mexico there was a meteorite hit, or I don't know what type of impactor it was that killed the dinosaurs. You guys would know what is place, right? And I can't pronounce it. Can anybody pronounce it?
Chicxulub, in Yucatan.
Yeah, that's it. Anyway, so basically, can you imagine the amount of energy generated? Such mechanical energy would actually make the bond break. If you were to take, for example, a steel plate and heat it to 2000 centigrade, and you throw a drop on top of this plate, guess what happens? All the bonds in the water would break. So that tells you that all the organic materials within impactors would have their bonds broken, and then eventually, when it cools down, it'll be reformed. And people seem to think that that such a bombardment would have played a part during the emergence of life. So I'm not going to read all these out, apart from I'm just simply going to show you reactions. Photolysis, radiolysis, just a fancy name. Although it's written radiolysis, actually I got to stop here. I just realized. I've written radiolysis, ionizing radiation they're talking about here. But of course, you can also make reactive oxygen by shooting, let's say, water droplet with electrons or protons or ions of your choice, and you will get to form some reactive oxygen species. Then there's Fenton reaction, ozone, lightning, and atmospheric reactions. So photolysis, this is what's going on during photolysis. At the 320 nanometer, you can break the ozone into activated. You can see where it says O2 and oxygen atom with star around on it. That tells you that's active. It will react with anything within nanoseconds. It will react in, and of course, when it reacts with oxygen, reacts with water, you get hydroxyl free radical. That's the dot with OH written. It's a free radical, and it's highly reactive. That radical that also reacts in seconds. There is something else. Oh yeah, I've written here O3. You guys might think, well, there was no oxygen on the planet Earth. This was the point I introduced in this slide, saying that the facts about NoRCEL, and also don't forget, if Sweetman, that's the last paper that I showed you, if you think about Sweetman, he said tons and tons of oxygen being produced on the seabed. Imagine that's happening during around 4.3 billion years ago. Imagine it's happening. And you'd have a phenomenal amount of reactive oxygen species. And also, don't forget that star, Uchipuchi, I can't say the word actually, but anyway, so that it would have been happening. So there is there would have been, but of course, the one thing about oxygen itself, and no wonder it's called reactive oxygen, is because it's actually highly reactive. Just only fluorine surpasses it, But life somehow chose this, and of course, who knows? Fluorine might have been involved, but if through chemical evolution, then biological evolution, then it's kind of got rid of eventually. So here I'm showing hydrogen peroxide breaking into free radicals as well. And here's radiolysis. Remember this. Radiolysis, all it means is that it actually, when you trying to break bonds, and when you're trying to break oxygen, it's the deeper electrons. You want to affect all the electrons. And this becomes more important when you consider astrochemistry. In astrochemistry, the reason I bring into that equation, because a vast amount of organic material was delivered onto the surface of the Earth. And during that impact, a lot of oxygen, a lot of reactive oxygen would have been produced. You can imagine how chemistry would have been taking place. Remembering that the reason you want reactive oxygen is that the energy is available. I mean, here in the audience, I can show you how it could be, but on the because I don't know whether am I visible on the by the net, Carrie? Am I visible on the net? Can you see me? Okay, everybody can see me, so I can do. I'm so sorry, I hadn't realized. Okay, actually, what happens is this. Imagine, let's do let me show you what happens to carbon. You can imagine what happens to the oxygen as well, carbon dioxide, I should say. Look, my body's carbon dioxide. If I move back a little, and my body is carbon, my fists are actually oxygen, okay? Now then, if as I stand here like this is the ground state, right? As soon as I go like this is the excited state. Ground state, excited state, ground, excited. The reason that happens is because this is called vibration. It happens at several different modes, but I'm not going to go through this. Every time a small amount of light hits my arms, energy gets absorbed, the bonds expand, because it can't stay there forever and a day. If I ask you to stand on one leg, you can't stand on your one leg forever and a day. Sooner or later, you'll have to put it down. So sooner this has to come down. When it comes down, it emits energy. And that emission of energy, actually, you can see it in your mind's eye, is being used to carry out reactions. Thank you very much. I hope you guys saw that what I did. And so radiolysis also produces various, they can even produce, if you look at the reaction after the arrow, it's e to the minus, that's saying there's electron being produced. AQ means aqueous, which means water. So there'll be electrons knocking about in water. And then you've got that proton with H plus proton, then you got free radical hydrogen peroxide, then you got dihydrogen. Normally, when we use the word hydrogen, people simply means, actually easiest way of saying it is like this. When we talk about oxygen, we actually mean dihydrogen or molecular hydrogen. But to chemists, hydrogen implies atomic hydrogen. That's proton and electron together. That'll be hydrogen to them. But to us public, when we talk about oxygen, of course, we're thinking breathing oxygen, that will be the triplet ground state oxygen we're talking about. But we don't actually say that. But technically, we really should say, oh, I'm breathing dihydrogen or molecular hydrogen. The reason I brought that into equation is that that's a dihydrogen you've got there. And it's stable, by the way. Hydrogen is stable in that state. And then you got H2, HO2. What is that? I think I've got it written down later on. I think it was a previous slide, something like hydro. It was in the previous slide. It was. I'm so sorry. I missed that. But I've forgotten. I'm so sorry about that. Okay, let's move on to the next one. And of course, I'm not going to read all this out. The UV light is involved. UV light can actually break bonds. Well, they can, because I've shown it here, 320 nanometers. So and in the process you formed dioxygen plus radical activated oxygen. And go back. There's nothing much I can add to the radiolysis as well. And Fenton reaction, this is to do with the metallic Ross production, reactive oxygen production. These are the reactions for the using iron. So if you add two, well, these are the reactions. I'm not going to, in the interest of time, I'm not going to read them. The point is, you've got, if you look at it, you've got hydroxyl free radical and hydroxyl ion being produced, both. Those will have a high energy. And of course, Haber-Weiss would produce, eventually will produce, again, it's just showing a long-winded way of saying that you can produce hydroxyl and a free radical and hydroxyl ions. And ozone reactions. So here's ozone being used to produce hydroxyl. I'm trying to illustrate a point. These radicals would have been so much so that you couldn't have ignored it at 4.3 billion years ago. So lightning would have, this is my favorite, lightning would have produced the same thing as well. So here you're talking about breaking nitrogen bonds and oxygen bonds in order to form nitric oxide, 2NO. And this shows you that something like the nitrous oxide is actually usually reactive, highly reactive as well. So these are some of the reactions taking place. There's nothing I can add in this other than important bit is the being nitrogen, nitric oxide being produced. That's the important bit. It's sort of saying that you spread in the wings. In this, I'm showing the oxidation reaction in the first one, reduction in the second one. So that means to say that reactive oxygen species cannot carry out redox reactions, not just oxidative reactions. And then it's also involved in protonation, meaning that you're adding a proton to it. You look at H+, that's a proton, and it adds to the superoxide and produces it produces this HOO radical because it's got a dot there, and it's called hydroxyl radical. There you have it, ladies and gentlemen. And flash photolysis of nitrite produces, again, nitrogen-free species. And then you've got, in the fifth reaction, you've got the two hydroxyl groups to produce, I'm just producing hydrogen peroxide. That it's just showing you various reactions, that's all. This, the 266 nanometer is actually more energy than the 325 nanometer I showed very early on, and which means that it would have actually split water in such a way that you got a proton being produced in hydroxyl ion. That's a very important point because that might have played a part in the emergence of life. And also in bracket, put hydrolytic. What the word hydrolytic means is that it produces two different types of species, meaning that it produces an ion and plus a proton and a negative hydroxyl ion. That's what it means. You get two species. Whereas if you were to split, say, nitrogen or oxygen into two separate oxygen or two separate nitrogen, that would be homolytic reactions taking place. And so role of prebiotic chemistry during the origin of life. Okay, right. Okay, so here we are getting a bit juicy here. Ross could have contributed to the oxidation and modification of simple organic molecules, leading to more complex biomolecules. For example, hydroxyl radical, my favorite word for the day, actually, keep coming back to me. It might even haunt me tonight. So hydrogen peroxide could oxidize methane. Methane is an organic compound to form formaldehyde. Formaldehyde. From this, you can actually form sugars, for example. Sugars can lead to form saccharides. In other words, di and tri and poly and so on, like starch. I'm talking about. Also, it could have helped make the pentoses. Pentoses are sugars that has 5 carbons, and they're used in RNAs and DNAs. And so you got prebiotic amino acid synthesis. Yeah, some rust-driven oxidation process could have helped convert nitrogen-containing compound like ammonia and hydrogen cyanide into amino acids. That I can see happening. But next time I give this talk, I will expand this further. So, example, oxidation of hydrogen cyanide into the presence of rust could lead to the formation of glycine, and that I can buy that. I can buy that, you know, and because the reason that is the hydrogen cyanide contains the necessary compound for glycine to be made. For example, the hydrogen cyanide contains hydrogen, carbon, and of course, oxygen would have been the reactive oxygen itself, and amino acid could have been easily made. And oops, I lost. What was the last one? Last one was RNA world hypothesis, nucleotide formation. It says there, yeah, it's possible to make primitive nucleotides. It didn't have to be all the nucleotides that are used by biology in the present day biology. That is cytosine, guanine, adenine, thymine, and uracil. So it would have been some other amino nucleotides. But as chemical evolution went on, as Darwinian biological type of evolution kicked in, they would have been replaced because efficiency would have been the byword of the day. So, yeah, this could happen as well for me, nucleotides. And versatility, this is a cool one, actually. It took me quite a while to write. I was even writing it this morning. Got up very early to write this. So look at the third column. At low pH, around about say 3, reactions is fast and produces hydroxyl radical and hydroxyl ion. And at neutral, it's very, very slow. You know, reactions are so leading to secondary rust, like for example, superoxide. Could be generated, and in prebiotic chemistry could take place near the volcanic event. By the way, there's a slide missing. I just realized. I didn't do the volcanoes. I don't know where that slide went. I hadn't done it. I can't remember talking about volcanoes. But anyway, let me talk now, just in case it's in a later on, but let me talk about volcano here. Is that volcanoes very important in the sense that there are 2 types of lightning. There's a lightning that occurs over a desert, and there's a lightning that occurs in the top of more or less volcanoes, and that dark material coming out of NoRCEL, not NoRCEL, volcanoes. It could be hydrochloric acid, it could be sulfuric acid, it could be carbon dioxide, carbon monoxide, it could be methane, it could be any other likely suspect coming out of volcanoes. And the electric lightning generated in those plumes is much more intense compared to the one over the desert. It's usually a bit lighter, and although it does produce lightning as a typical classic lightning sound and all of that, and also heat and light, but here you'll be breaking bonds in, say, sulfuric acid, so you'll have a sulfuric species, reactive species, but sulfuric acid contains oxygen as well. All of these, there would be real solid chemistry going on there, and in the volcano is very, very important. I think this idea put forward originally by Darwin that at the foot of, well, he didn't say actually foot of a volcano, he just said puddle, in a puddle, and some gases coming through, but it didn't. I don't think he used the word volcano next to, but I'm using it that it's at foot of a volcano. You got a puddle of water coming through, and all these ions, all the reactive species bubbling through. Remember that I said there's a carbon, chlorine, nitrogen. Yeah, So you saw that earlier on, and oh yeah. Okay. So nothing to do. I've got nothing more to say about catalysis of H2 hydrogen peroxide. It's all there. It's more to do with the melting ice and some of the hydrogen protected in that, and that would have been sort of irradiated by radiation, and would have converted into various reactive species, and these could be possibly present on Europa, for example, one of the moons of Jupiter. I think it's Jupiter. But anyway, you can also find a hot temperature environment, thermal decomposition of hydrogen peroxide. And if you read the third one, high temperature, useful in explaining oxidative chemistry in hydrothermal vents, and especially on icy planetary body. And again, there's I've written photolysis twice. That shows how much pressure I was run under to get this prepared this and of course this PowerPoint. And of course, this is to do with, actually, I just remembered, the temperature cold. This is at low pressure, atmospheric pressure. That's why I'm showing them. There's a slight difference. These are produced radically, in this case, photolysis. And I haven't given, that was a photolysis of peroxide. Oh, okay. Okay. So in low pressure of oxygen, in the very early Earth, 4.3 billion years ago, you would have had still been produced reactive oxygen species. And I'm building up a real big network now. And then, of course, if you got oxidizing atmosphere at the bottom line, and the reaction becomes even more exciting. In this case, 240 nanometers HV light does some chemistry. It goes from the two oxygen radicals. I didn't put the dot there. I should have put the dot to carbon to producing dihydrogen, and that producing two ozones. So ozone may have been present on the very early early Earth, and revisiting Fenton reactions. And I don't want to repeat these. You can see these reactions. The important thing is that this is what I drew earlier on. So I'm going to show you a pathway. One of the pathway which I'm sort of speculating that might have happened. And here it is. And here's a close-up of it. Here's a close-up of it. So this type of reaction may have occurred. There is a very important, ladies and gentlemen, a very important point here. I don't know whether you can see sulfur, which is yellow, down at the bottom with an arrow. That actually is equivalent of hydroxyl group in carbon chemistry. Thiol is important in carbon chemistry. The thiol group is important in that it forms sulfur bridges. So if you were to make a chemistry, like for example of peptide. By the way, we never speak of proteins. Proteins are the wrong word to use because proteins are modified, highly modified, biology produced poly chains, you know, whereas peptides and polypeptide and oligomer, that is randomly made. Protein is made to specific instructions from the DNA. So never confuse the two. Always speak of peptides when you're speaking about the emergence of life. So basically so let's assume, let's do a thought experiment. Suppose we produced some sort of a peptide with which has a amino acid that has sulfur in it. That amino acid is called cysteine, and it would have actually combined with nearby another cysteine to form a sulfide bridge. Does that make sense? Here's a protein one. Here's a peptide one with cysteine amino acid. It's hydroxyl thiol group is hanging down, sake of argument. And here's another peptide with a thiol group pointing up. They could react together to produce a conjugate protein. Peptide. Okay, you know where this is going. And also, of course, you'd have, I've written a paper, ladies and gentlemen, on this. It's called The Way Forward for the Emergence of Life with Freons. Please have a look and you'll learn all about these disulfide bridges and stuff like that, published in 22. Yeah, have a look at that and you'll see what I'm talking about. So, oh yeah, like the other amino acid, very important amino acid in peptides is proline. Proline is a flat molecule. What do I mean by flat molecule? You know, if you look at any other 19 amino acids, amino acids of used by modern by biology on Earth, they all can rotate about its axis where the bond is, the peptide bond is, sometimes also called amide bond. They can rotate. They rotate like this amino acid. So the protein can rotate any which they want to, right? You can rotate them about. But with proline, if proline is present, it stops the rotation because there's a double bond in it somewhere, right? In its structure, that it prevents it from rotating it. And that is important when you're making a U. You got a peptide, you want to make a U. Where the U, bottom of the U is, you would have something amino acid like aspartic acid and glutamic acid. Both aspartic acid and glutamic acids are involved in making bonds and breaking bonds, because they have both carboxylic acid group as well as alcohol group. So basically, you would always find these two amino acid at the where this U bond is the active site in proteins would be, but I'm talking about peptide in this case, right? And you would want the proline to be sitting in center somewhere there, so that it forms this crucible where you can actually carry out your reactions. By the way, you don't need longer than, say, for example, I don't know, 12 amino acids, maybe at the tops. You can actually you can go as low as 3 amino acids. They're called triads, by the way. So there you have it. You've got all the chemistry you need to form life. If we hadn't had a problem with the getting going, I would have taken a little bit more time to explain things. So hydrogen peroxide. So my friend Rowena Ball and her colleague John Brindley, they wrote a paper in 2018, and they said that hydrogen peroxide sort of acts as a clock, sort of oscillating, a bit like BZ reactions. I don't know, it's a long Polish name. I can't seem to pronounce them. But just check BZ reactions, okay? And you'll get the idea that radix would be oscillating, and it would have. It's a very nice paper. You should read it if you're interested in life. Just put the paper is called Hydrogen Peroxide Crucible Hypothesis at 2018, Ball and Brindley, and you'll find it really exciting that. And so here's the paper that they published in the 2019, although I said previously 2018. But anyway, we're all human. Every now and again, you do make mistakes by saying silly things. So anyway, the conclusion is that in a way, I didn't talk about the negative aspect. There are naturally, like any other chemistry reaction, there's always downside to it as well. And downside to it is the Ross may cause. I should have put word like may cause molecular damage. You know, it's not. Always keep things aloof. You know, and so this is the end. So I've actually come to an end. Thank you very much, everybody. I'm sorry for the late start. I'm sorry for meddling about. I'm sorry if I spoke very fast. I'm sorry that oh God, I'm bored. I'm sorry for being sorry. How's that? Okay, thanks. Thank you very much. Yeah, I don't have a final thought. I've spoken enough. Thank you very much. Anybody got any questions? Yeah. Hi, Jose. Thanks.
There are two well-known biological processes in which ROS are produced, and they are aging and cancer.
Yeah.
So, if someone has cancer, that is a process of aging. And aging is the cause of not having cancer.
Yeah.
And you have ROS in both cases. That is not the origin of life, but
Yeah, I mean, this is why I said it's double-edged. But I think you'd have to explain how is it that this energy is available regularly, repeatedly, in the same amount all the time. And Ross would do it. would do it in relation to saying that bringing the cancer and aging into process, but that's biological doing. All the rest that we know of, the thousands and thousands of papers are published. It's too many for any one person to read them all. And to be quite honest, I don't consider that to be part of this conversation, because what we're really interested in is that how was those reactions taking place. Actually, I said it in one word in passing. It's a network which I'm working on, and it's not actually finished, that network, and I couldn't bring it out because it's complex. You know, it's a network, and every reactive oxygen species what we need, we have to make it abiotically. Yeah, we have to make it abiotically, and yeah, and that's why I wouldn't talk about anything to do with biology, basically. That the one, the diagram, the diagram I showed you right at the end, it's actually from another point of view. It is taken from biology, but what I did, took off the enzymes. I worked it out, you know, because enzymes are not weren't available then, you know. Yeah, so that's it. Yeah.
It's not a question, but so we can think on Ross as the two sides of the same coin.
Yeah.
We said, because we have on one side, as you exposed, as you show us, a kind of a spark, to originate or to contribute to the origins of life. But also we have, as Marco says, and as many biomedical researchers know, that growths are very damaging to cells nowadays.
Yeah, whilst that's true, but remembering that at the time, the biology didn't exist. What was needed actually, and this is why I also try to say to you, is that all the reactions, like if you were making proteins in your body, right? If your cell is dividing, when you're storing your energy, all of these are actually requires endothermic reactions, right? So which means that they would generate water. And also the product form is at a high energy. So energy that you have to give in, you have to bear that in mind. It has to be any less energy than the bond requires to be formed. It wouldn't form that bond. So life would have had to come forward with something. There must be something like it's not just the reactive oxygen species. I'm also thinking now about nitrogen reactive species as well. Collectively, they would have actually formed quantas of energy. I know a lot of people, physicists, might go crazy on this. Oh, you're using our word quanta. There would quantas of energy, because you need the same amount of energy each time to form dimer. Yeah, it may be that I haven't looked at the thermodynamics of that in the sense that would, let's say, glutamic acid and aspartic acid forming dimer, and then you got glycine and proline forming dimer, would it be the same amount of energy? Of course, one would argue that because it's amide bond, then energy should always be the same. But in this case, whereas you use the word proline is slightly different. And there are others where the protons are available or not available. I can't remember which amino acid. So the energy, I think, might be slightly different. But in biology, it may be the same because it's made by a machine. but in abiotically, it would be slightly different. A different amount of energy each time. So these collective, these carbon reactive species, nitrogen reactive species, and the oxygen reactive species, they all might have colluded to produce a first, maybe a protein. That particular peptide would have produced a peptide, oligomer for that matter. In fact, peptide is too long. Oligomer is up to 10 amino acids. So basically that would have produced small peptide, yeah. And that's easier to make, you know, and it would have, and it would answer get away with this quanta of energy needed to make these bonds every time. And each one of these reactive species from different elements might have worked on it. And personally, I'm very, very excited about it. The first time I come across reactive oxygen species, that was in something 23 years ago. Professor Nick Lane from the UCL, University College London in the UK, wrote a book called Oxygen, Molecule of Life. And at the time, I was excited about it, but time had passed. And then Professor Rowena Ball, whose paper I showed, said to me, Sohan, are you interested in reactive oxygen species? I said, yeah, I'm interested. Tell me more. And they talked about Nick Lane's book and stuff like that. I said I was interested then, I'm still interested. And so we started talking about it. And it led to this point, me investigating all the time and filling up my flip chart. You know, I think on flip charts. You know, I draw things on flip chart and it's sitting on the table permanently. You know, so basically, I'd like to now look at the and bond formation. By the way, it's very difficult. It's not rocket science. It's very, very, you don't have to do an experiment. You can actually work it out from the bond energies, you know, and you say, well, in one respect, if you really think about it, you've got carbon from carboxylic acid and from amine group on the other side, on the other amino acid, and you can combine them. And the bond is, amine bond is always the same. So I suspect that it would be the same energy. And then we can actually work out the energy. For example, the excited state on the superoxide or hydroxyl, these, it's about 1100 kilojoules, I think, per mole. Yeah, that's how they calculate it. Yeah, so if as you come down, there's about 600 joules of energy also given out later on as it falls. The excited state means that although it doesn't look so, it looks like I'm speaking some alien science, but it's not. You know, it's a perspective on it. You're talking about raising electrons to a particular level. So when I was showing you the diagram, it's raised to a particular level, you know, and if you saw the very, very high, really, really above, with the pi bond right at the top, they were right at the top. On the side of it, you guys might not have noticed, and I didn't say it. I apologize internationally. I didn't say it, that as it goes up, the energy increases right at the top. And if you were to increase it, if I go back, Oh yeah, here it is, right? I mean, look, you got another sigma bond up there, right up there. There, you know that empty box sigma star. You know, if you put energy, some electrons into that, it will actually even have a greater energy. So what's happening in reality is that it's at a certain level, and this is a 2p level, by the way, all of them, and that's a 2s level and 2p level, you know. So the rays, and they're actually falling to its ground state all the time. You know, ground state in this case was so. Let's say that's a radical. That particular is a radical, okay? As it is, it's a radical, and if you were falling down, it's falling down this to this state. The difference between that, what was it? That was the hydroxyl radical. That was hydroxyl radical, right? It's falling from hydroxyl radical to this state. This is the stable state. So when energy hits the electron bond, what energy hits the oxygen bond, it goes to this state and then this state. So it's going to fall from that state to this state. So that's the energy we're talking about that would have been used for making bonds. That's all. That's the thing that we're always talking about. But if you take it to sigma level, you know, I know no other example, but it's not impossible in science. Everything's possible if you try hard enough to put some electrons in that. Whether other people have done it or not, I have no idea, you know. And so that's what I wanted to explain. You know, when in Lewis, when you do the Bohr, Niels Bohr's orbital diagram, it's like electron from here jumping to that. As it falls down, it gives out energy. That's it. That's what it is, ladies and gentlemen. And do stick with NoRCEL, and you'll find that you learn a lot more, and especially in this. And in 2026, that next year, we will actually have possibly have a Reactive Oxygen Species Part 2 conference. And perhaps you guys would like to come to that, because I made a decision that we are going to actually explore reactive oxygen species as well as the other ones as well. So we will actually find people who are working in this area, although there are not many, but there are some cookie sort of people that are maybe working like me, you know.
And yet the precise origin of life, for example, we the theoretical biology group are convinced that life started with a genetic code when those nucleotides and those amino acids began to be translated. Well, from the nucleobases to the amino acids to form the peptide, because all of this is the sparkling, the start.
Yeah.
But the precise origin of life remains so elusive, and that's fascinating too.
I don't disagree with you what you said, actually, to be quite honest. Ladies and gentlemen out there, what Miriam said was that the life sort of began with the genetic code, some sort of coding system, that some sort of memory tape, you could say, that passes on to the next generation. But where does reactive oxygen species fit in is before that to form the nucleotide. You needed to make this. And for example, as I pointed out, sugar, 4-methyl aldehyde is the monomer of sugars, basically. And to make the pentose sugars, all you need is formose reactions, and you can make peptide, these 5 carbon sugars very, very easy. And that would have been used in connecting to 1, 2, 3, third carbon on the peptide, on the sugar, and then to the 5th one on with the next nucleotide. You needed that, you know, so you needed these things to happen. But once it's made, it's made, you know.
All the ingredients together to form life.
Yeah, yeah. Okay.
Thank you very much, Sohan.
Yeah, you're welcome. Thanks, everyone. If you're still with me, thanks.
Okay.
It has been a pleasure listening.
Yeah, yeah, actually, each time I think
Sí,
I have actually beginning to understand myself as well. Do you know what I mean? What's needed? Yeah.
Let me give you some bookmarks with
Recording stopped.